So let's talk about VDBs and how we can use VDBs to create collisions inside Houdini. So to start with, what I'm going to do is I'm going to take the extruded version of my cliff geometry here and create VDB out of it. Now for simple geometries like this, it's as simple as just dropping down a VDB from polygons and literally connecting these two and having a VDB volume out of our geometry. That's it, done. It looks good enough for its resolution. So voxel size, if you increase this voxel size, it gets lower res. If you are running low on memory, or if you have less resources in your system, it's advisable to play with the voxel size until it matches the specification of your computer. But for this example, I'm going to do 0.1 because I do want those really nice details, and when our water collides with this cliff, it should have really nice collisions. Right, and literally putting another null down and saying out cliff VDB. Now we're going to take a look in a minute on how we can call this VDB inside our .NET. But let's talk about our ship geometry now. Now the cliff geometry was very simple. It was a full enclosed geometry, and we just dropped a VDB down and it just worked. But this geometry is very complicated. It's got a lot of parts to it. It's got a lot of planar geo to it. It's got a lot of non-enclosed geometry to it, because VDBs do not work on planar geometry. Case in point, if I go back to my cliff geometry, and if I look at the cliff, which is the non-extruded cliff, so like a planar cliff, it's not enclosed, and I connect my VDB onto that, you would see it's not going to give us what we want. It's all over the place. It's not doing its thing. So VDBs do not work on planar geometry. And that's where we run into an issue with our ship geometry, because our ship geometry is a lot of pieces, and most of them are planar, or most of them are not thick enough for VDBs to work. So what's the solution? Well, what I've done here is I've done a simple example of tetrahedralizing a geometry. So I took a sphere, which is a polygon mesh, and I blasted some faces out of that sphere. So essentially it is not an enclosed geometry anymore. And then I click, and then I put down a tetrahedralized node, and what it did was it essentially enclosed all those empty spaces and converted the geometry into this triangular mesh, and that's what we want. So let's try to do that to our ship geometry here. Again, this ship geometry is complicated enough that we shouldn't tetrahedralize this all at one go, and this is where the use of for each loops come in handy. So what I'm going to do, I'm going to press tab and type in for each, and we have a bunch of options here. I'm going to pick the top one, which is for each connected piece. And what this is going to do is, as soon as I connect my geometry to the connectivity SOP, and it's going to create an attribute called class on each and every individual primitive that are not joined together. So if I go to my geometry spreadsheet, you can see there is a class attribute that is categorizing our geometry that are not together. So 0 to 424. So there's literally 424 different pieces in our ship geometry. And what we're going to do is we're going to take that attribute and run it through a for each loop. So if I run it through that, you can see that it has isolated this one piece. And what I'm going to do is I'm going to drop down a tetrahedralized node right here, and I'm going to change a bunch of options here. So the output, the mode, I'm going to set to convex hull, so it's going to enclose it. So there you go, our geometry is enclosed, but I don't want anything on the inside. You can see it's creating geometry on the inside. So the output, I'm going to set it to polygons. Right, now we have an enclosed geometry. And if we run this loop on all those 400 odd pieces, it's going to do that for every single piece. But obviously you can't see it because our normals are weird now because we tetrahedralized everything. So I'm going to drop down a facet sub and say post compute normal. Voila. So now we have a very good looking geometry that we can convert to VDB and have our VDB collisions working. Now it's a good idea to drop down a VDB from polygons. There you go. Super simple. If you had to try VDBing the entire geometry here, it's going to be a mess. It's not going to be stable, and some parts of it would be weird, and it would be also slow to compute. But this way, tetrahedralizing the geometry itself gives us the ability to VDB it without losing the shape of our ship geometry. And I'm going to decrease the voxel size to have more voxels, to have a little bit more resolution to our ship geometry here. And obviously it moves and everything with it moves. Alright, now it's always a good idea, because it's VDB, it's always a good idea to save this out, and I have done that already. So ship VDB, not that, and that should be reading our cached out VDB. And I'm going to say null and out ship VDB. And I'm going to rename this null. Okay, this is out ship geo. Right. So now, how do we call these VDBs, the Cliff VDB and the ship VDB, into our .NET for collisions? Before we jump into that, I would like to talk a little bit about this very important thing. So, the ocean source node, we have our points here, and our points are going inside this cliff geometry, which we don't want. We don't want the points inside the cliff geometry to go to waste. That's a waste of resources. So how do I delete those points? Well, it's super simple. I'm going to go to my cliff geometry, copy this null out cliff geo, the extruded one, mind you, and object merge that geometry right here. Okay. And I'm going to connect the output of that to the second input of my ocean source, which is collision geometry. As soon as I do that, Houdini would cull the points from inside of the cliff. That's it. That's all we need to do. And obviously, a couple of things to also note here is the resolution. Obviously, the higher this number, the lower the number of points you would get in your simulation. So 0.2, let's say, would give you 1.9 million points and 27 million voxels. And as you decrease this, both of these numbers, they go up. So you would see it would give you around about 3.5 million points and 64 million voxels in the surface field, which is crazy. So sometimes what you do is you use this option called oversampling. And what I like to do in the .NET under the particle motion, under the receding, the surface oversampling, I like to copy this parameter and I like to say paste relative references here. And essentially what this would do, let's say you don't want to increase the voxel count, but you do want to increase the point count. This is where this oversampling setting come in handy, because you can essentially increase this. So let's say if I have to check this off, you will see our points would decrease, so 1.7 million, but the voxel size did not increase or decrease. And if I check this on, again, the voxel size will remain the same, but the number of points would increase. So it's a good idea that if you do want to, increase only the number of points, it's a good idea to just use the oversampling rather than the particle separation. Right, now on to calling in our collisions in the .NET. I'm going to drop down a static object, 2 of these. So one for cliff, one for our ship. Going to drop down a merge sub just above gravity and disconnect that. Static object 1 goes to merge, static object 2 also goes to merge, and flip solver also goes to merge. And I press L to sort out the nodes. Right. In the subpart, let's call in our cliff geometry first. So cliff geo, out cliff geo. Cool, we have our cliff geometry here. But now I want to call my VDBs. So under the collisions tab, under the volume tab, we need to make sure that the mode is set to volume sample, because if it's not, when we call in the VDB here, Houdini is not going to recognize it. So out cliff VDB. So proxy volume, we tell Houdini, okay, pick this VDB and treat this as a collision by switching it to volume sample. And we're going to do the exact same thing with the out, let's say ship geo. So out ship geo, and then collisions, volumes, volume sample, and proxy volume, we're going to pick up the out ship VDB. And because the ship VDB or the ship geometry is moving, on the static object, I'm going to check on use deforming geometry. So it's going to recalculate this geometry every frame and take into account the animation of our ship into the simulation. Now what I want to do is, I want to do a flipbook before we dive into the next chapter and talk about some settings of the flip solver. I want to do a quick flipbook to see how our simulation is looking just by setting up these basic parameters.